All right. All right. Okay, so where were we? We can close this, we can close this, we can close this and this. What's this? Destiny. Yeah, that's not important. Uh Bell's inequality. I give up. I just give up. I mean, everybody.
Different. Niels Bohr, one of the founders of modern two of the biggest intellectual giants of modern physics changed our view of reality and proposed their theories around the same time in the early 20th century. Yet their views about reality were completely different. Niels Bohr, one of the founders of modern quantum mechanics and the father of the Copenhagen interpretation, argued that reality, or the state of a particle at the fundamental level, was not only unknown, but was unknowable until it was measured. Albert Einstein passionately disagreed with this idea and believed that reality was knowable, and that probabilities could not completely define reality, that there had to be an objective reality out there, independent of measurement. He famously said in his dramatic statement, "Do you really believe the moon only exists when you look at it?" Bohr and Einstein argued passionately about their views on the essence of reality, and for 30 years, both views were considered equally valid, and scientists chose sides.
Both views were considered valid or equally valid. So one guy says the moon exists only when you look at it. And the other one says, "Are you out of your mind?" That's equally valid. That's equally valid. Listen, it's equally valid. Equally valid. Equally valid. Equally. It's just as valid. It's valid. It's just equally valid. What do you mean? The moon is there only when you look at it, and the moon is there all the time. Equally valid. Equally valid. They're just as valid. And not only that, they used to be equally valid, but now we know Einstein was wrong. Now we know Einstein was wrong. The moon is not there when we're not looking. Now we know. Einstein was taller than Bohr? No way. Bohr was a football star, by the way. Bohr and his brother were soccer stars. So I think they were giants. I don't know how tall, but how tall was Einstein? Oh my God. He's really short. He's tiny, 5'8". That's tiny. Okay, Bohr. There's, how tall was he? There's no data on how tall he was. So we don't know how tall he was. I don't know. I don't know how tall he was. I'm really curious because he looks tall. Looks like a football, like a soccer guy, like a giant. I think he was a goalie. Goalies are usually giants. Like the bigger a goalie is, the better, right? The better he is at blocking the goal. The goal. Yeah. Let's see. Tall. Mentally, no. How tall? No. So there's no information. Look at his wife. Wow, she's gorgeous. Jesus, she's hot. Jesus, that's a hot chick. Amazing. All right.
And in 1964, Irish physicist John Bell devised a way to prove whether Einstein's view of a classical deterministic view of reality was correct. And he put this in a simple, elegant equation called the Bell inequality. Although the equation is simple, understanding what it means is not so easy. So how did this simple equation disprove the ideas of the most famous and powerful scientists of the 20th century and forced us to confront the unsettling truth that we may live in a fundamentally non-deterministic universe? The answer is coming up right now.
All right. So, Jack, there are people who believe in that. Basically, moon renders only when you look at it to save memory because all this is a simulation. Hmm. Yes, Jews are short in general. Really? Einstein was shorter, but they used to measure people in shoes plus the hair. Hmm. What about Einstein's wife? She was an actual physicist. I mean, he banged a lot of chicks. As far as I know, Einstein was banging everything that wasn't nailed to the floor. How many chicks did Einstein bang? Let's see if Wikipedia covers that. Is there imagine a Wikipedia just for that? Bangipedia. Based on the provided source, there is no direct answer to the question how many chicks did Einstein bang? As the term chicks is a colloquialism typically used to refer to young female birds, really. In a more informal sense, young women. The search results focus on Einstein's family education. Well, part of his extended family is the chicks that he banged, especially up the Tushi. I think he used to be extremely fantastic at that in professional life, but did not provide information on his personal relationships or romantic conquests. Ah, romantic conquests. What's a romantic conquest? When you put your pee in her tushy, that's a romantic conquest. However, according to one core answer citing Einstein's personal letters, he had at least 7 girlfriends. Jeez. Simultaneously during his second marriage, which were published in recent years. It's essential to note that this answer does not provide a definitive count, as it only accounts for the girlfriends mentioned in published letters. That's only the ones we know about, and may not represent his entire romantic history. Jesus Christ. In conclusion, without further information or primary sources, it is primary sources bring the chicks before us. It is impossible to provide an accurate answer to the question of how many chicks, young women, young ladies, Einstein dated or had romantic relationships with. I'm not asking about the romantic relationship. I'm talking about banging. The available data focuses on his family and professional life rather than his personal relationships. Mhm. Well, there you go. That's the answer. How many girlfriends? Answer. At least 7 separately mentioned. At least in letters, like documented 7 simultaneous or something. Anyway, during the marriage, during the marriage. So there you go. So set your standards high, gentlemen. Uh, what do we got? What do we got here? First wife. What about Einstein's wife? She was an actual. Let me see his actual wife. Let's see. Einstein's wife. Let's see the wife. Einstein's waifu. It's difficult to tell because she might have had a good body. We wouldn't. She had a big nose, but with chicks, it's really not important. And like there's many parameters. I mean, maybe the face is maybe she's not so hot, but maybe she had a good, maybe she had, maybe she compensated. Face is not critical. I mean, she was not pretty, but she was a good mathematician. Anyway, his second wife, I think, was his cousin, was his first cousin or something. First cousin or second cousin? Okay. Let's see what else can we close. Yeah, it's not critical for now. Let's see this.
Prize winning proof for quantum physics proves two fundamental principles of Advaita Siddhanta.
We'll come back to this.
And so, in essence, Einstein was wrong in his EPR paper, and this led to groundbreaking work later on
Einstein was wrong in his EPR paper. Okay.
from Elaine Aspect, who was able to perform even more tests of Bell's inequality and close some of the loopholes, so to speak. And then this led to Anton Zellinger, who was able to show.
But she's just asserting. She's not explaining anything. I mean, is she supposed to explain? I mean, no one explains anything. Everyone just asserts. It's just assertions. This is so boring.
The demonstration for the first time of quantum teleportation, which is not what you might think. It's not at all like Star Trek. People are not teleporting across.
Yeah, it's not. It's not at all. It's just quantum teleportation. It's not at all what you think. It's just quantum teleportation. Hey.
The room. But instead, quantum teleportation is a way to entangle or correlate quantum particles in such a way that you can transfer quantum information from one to another. So in order to really understand
while violating the speed of light, which is fine, apparently.
Why this is so important and why this is so groundbreaking, I want to go back and look at a very specific demonstration of Bell's tests for you. There are, in fact, many different Bell-type theorems that can be shown, but we're going to look at really one specific one today, which is called the CHSH test, or the CHSH Inequality. And so what you need to do for this thought experiment is first imagine a person named Alice and a gentleman named Bob, and they are standing some distance far away from one another. And then there's another guy in the middle, let's just call him Victor, and he's going to send a particle to Alice and to Bob at the same time. And Alice and Bob are going to perform, every single time this happens, one of two measurements. They're going to either measure the X projection or the Y projection of this particle. And so you can only measure one at a time. So in order to have a good understanding of the measurements of both, they have to perform this experiment multiple times. And it's important to know that every time Alice receives a particle, Bob also receives a particle. And again, the only thing really assuming here is local realism. So these particles are not moving faster than the speed of light. Bob and Alice can't call each other faster than the speed of light and communicate information, nothing like that. And these particles also have these definite values that are either going to be 1 or -1, because let's just say they're normalized. So the values for X and Y for Alice and X and Y for Bob can only be 1 or -1. They are binary. So now at this point, we need to write down what is known as the CHSH value. So this is like so. Alice's measurement of X times Bob's measurement of X plus Alice's measurement of X, Bob's measurement of Y, Alice's measurement of Y, Bob's measurement of X, and then you subtract from that sum Alice's measurement of Y and Bob's measurement of Y. And it really doesn't matter where this quantity comes from. The fact is, if we look at it a little bit closer, we can factor out the Alice quantities from the Bob quantities, and you see.
What is she talking about? Alice X. So there's X and Y. I don't know what she's talking about. It's like they. Where are they going with this? They're just. My intuition is they're just confusing themselves. They're confusing me. I don't know what's going on already. They're measuring X and Y about the particle. I don't know what's going on. I'm already lost. What does it mean to measure X and Y about the particle?
They're measured the X projection or the Y projection of this particle. And so you can only measure one at a
An X projection or the Y projection of the particle? Oh, I don't know what that means. The X projection or the Y projection of a particle. What is the X projection or the Y projection of a particle? Like how wide it is and how long it is, I guess.
At a time. So in order to have a good understanding of the measurements of both, they have to perform this experiment multiple times. And it's important
What does that mean? I don't know what she means.
to know that every time Alice receives a particle, Bob also receives a particle. And again, the only thing really assuming here is local realism. So these particles are not moving faster than the speed of light. Bob and Alice can't call each other faster than the speed of light.
Local realism, no, locality means nothing moves faster than light. Realism means things. I'm not sure what realism means.
Information, nothing like that. And these particles also have these definite values that are either going to be 1 or -1, because let's just say they're normalized. So the values for X and Y for Alice and X and Y for Bob can only be 1 or -1. They are binary. So now at this point, we need to write down what is known as the CHSH value. So this is like so. Alice's measurement of X times Bob's measurement of X.
So Alice measures in the X direction, and Bob, I don't know. I don't know. I don't know what she's talking about.
Plus Alice's measurement of X, Bob's measurement of Y, Alice's measurement of Y, Bob's measurement of X, and then you subtract from
Alice X, Bob X, Alice X, Bob's Y, Alice Y, Bob's X.
that sum Alice's measurement of Y and Bob's measurement of Y. And it really
Why do you subtract A, Y, B, Y? I don't know.
doesn't matter where this quantity comes from. The fact is, if we look at it a little bit closer, we can
Doesn't matter where this comes from?
factor out the Alice quantities from the Bob quantities, and you see we would get something like this.
So this is, it doesn't matter where this comes from, something. And then bx is here, so you have ay and ax, and by you have ay and ax.
And I drew this for you here, little equal sign there again. So you can see that either this value every time the experiment is performed or this value is going to be equal to 0 because
What?
either you are measuring 1 minus 1 or you're going to have minus 1 plus 1.
Okay, I don't know. I don't know what she's talking about. Like, I want to skip it, but I don't want to skip it. I don't
The
know where
values
she's
again will be 1
going with
minus 1.
this.
So the maximum value this quantity could take on is equal to,
Why can this be? What is she talking about? What is she talking about?
2 at most. But remember, we're running this experiment many, many times. So say we ran this experiment, hundreds of times, and we're measuring a few different values every time Alice is measuring x and y, and a few different values every time Bob is measuring x and y. That means that this is actually bounded by 2 again, but it can be equal to 2 or less than 2 once we take the averages, and that's what these little brackets mean here. We're going to take the average of all of these measurements.
The brackets mean you take the averages. What?
All right, so this value has to be less than 2 if the only assumptions we are making are locality and realism. However, let's think about this experiment again, slightly differently. Let's now assume that instead of a particle, just a random object, Alice and Bob are receiving, they're going to be receiving entangled qubits. These are qubits. It doesn't matter how they were entangled originally at the beginning. Let's just say that they are. What you're actually going to measure, once you perform this experiment hundreds of times, is that this quantity is going to be approximately 2.8, not 2, not less than 2. We know for sure that 2.8 is greater than 2, which means that if these qubits obey the laws of quantum mechanics, which we know they do, quantum mechanics violates Bell's inequality. It is incompatible with local realism. So either something is moving faster than the speed of light, or these particles do not have definite values before they are measured. And now a lot of people, I think, misconstrue what this actually means. Some people think that this opens the gateway for faster than light communication. This is not the case. Let me be very clear about that, because this is a really easy mistake to make. Bob and Alice are not communicating with each other faster than the speed of light. There's no possible way to do that. The particles become entangled, and when you measure them, say Alice measures 1, we know that instantaneously the other particle is going to choose the opposite correlated value, -1. But that does not mean that Alice and Bob are able to communicate with each other faster than the speed of light. No information is being transferred at that speed. So that's really important to know. And since there's no evidence of anything in the universe traveling faster than the speed of light, the way that most scientists have interpreted this is that we have to give up the idea of realism. These quantum particles actually do not have values that are specific to them before you measure them. They are instead described by what Einstein called and resented the wave function. And so it has some probability of being in either state 1 or -1 before you measure it. And you might be wondering, where does this 2.8 number come from? Certainly, it's greater than 2, and we can understand that it does indeed violate this inequality, but where does this 2.8 come from? And so if you're interested, I challenge you to go online to the Qiskit textbook, and the link is linked below in the bio, and to try your hand at this experiment for yourself right now. There's a tutorial actually already published online on the Qiskit textbook on the CHSH inequality, and you can run the experiment from your couch or wherever you are right now and see indeed that you are going to get a number that is approximately 2.8. And while you might not win a Nobel Prize for doing this, because lots of experiments in this vein have been done at this point, I still think it's miraculous that we have gone in a few decades from an experiment that is Nobel Prize winning to an experiment that you can do, that I can do, from anywhere in the world. So what this showed is that quantum mechanics is even weirder and even more mysterious than we initially thought it was. It's completely incompatible with any classical theory that we can come up with if you assume locality and realism. And reading this, you might think that makes no sense, that's impossible, I hate it. But what these gentlemen who just won the Nobel were able to do is read this proof, this thought experiment, and then go to the lab and actually demonstrate it in real life. So it's not just weird on paper, it's weird in the real world. Quantum mechanics brings us to the brink of the impossible, and it brings us to the point at which we shouldn't be able to fully comprehend what's going on, but no further than that. And so that's why it's just a really, really exciting time for us in the field today, because these scientists showed that not only is quantum mechanics weird and mysterious and counterintuitive, it is practical. And everything that we're working on today at IBM Quantum, everything that other quantum computing companies are working on, quantum sensing, quantum cryptography.
Oh, she works for IBM. I think this Qiskit, I think, is maybe an IBM project. Yeah, this is IBM.com. So she works for IBM. She probably is getting $1 million a year.
Are all built.
No, she's not. Probably $250,000, 400K a year, probably.
On these experiments, which showed for the first time that entanglement, quantum entanglement, really is something that is so fundamentally different than classical physics can describe. So I want to wish congratulations to the Nobel laureates again from myself and everybody here at IBM, and thank them for their work and for our jobs as well.
Jobs. I don't know. She didn't explain anything. Nothing was explained. Nothing was explained. She just said, go look at the tutorial. So she gave a link to the tutorial. Here's the tutorial. So when I first asked ChatGPT to write my code, it used Qiskit. That's how I know about Qiskit. And I told ChatGPT, don't use any library. Do me a favor. I don't know what it's trying to do. I mean, I wish I knew what they're trying to do. What are they trying to do? My intuition is they're obfuscating the 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 problem to such a point that it becomes impossible to understand it and prove it or disprove it. In this tutorial, you will run an experiment on a quantum computer to demonstrate the violation of the CHSH inequality with the estimator primitive. The CHSH inequality, named after the authors Clauser, Horn, Shimoni, and Holt, is used to experimentally prove Bell's theorem. 1969. This theorem asserts that local hidden variable theories cannot account for some consequences of entanglement in quantum mechanics. The violation of the CHSH inequality is used to show that quantum mechanics is incompatible with local hidden variable theories. This is an important experiment for understanding the foundation of quantum mechanics. The 22 Nobel Prize for Physics was awarded to Elaine Aspect, John Clauser, and Ton Zellinger, in part for their pioneering work in quantum information science, and in particular, for their experiments with entangled photons demonstrating violation of Bell's inequality. Before starting this tutorial, ensure that you have the following installed. All right, I'm not going to do that. Map classical inputs to a quantum problem. For this experiment, we will create an entangled pair on which we measure each qubit on two different bases. We will label the bases for the first qubit A and alpha, and the bases for the second qubit B and B. I don't know. Oh, A and B. This allows us to compute the CHSH quantity S1. S1 is A times B minus B. I don't know what they're doing here. Each observable is either plus or -1. Clearly, one of the terms B plus or minus B must be 0, and the other must be plus or minus 2. Therefore, S1 is equal. I don't know. I don't know. I don't know where they're going with this. I just don't know. I don't know. I don't know. What is going on here? Well, what is this? I don't understand. If quantum mechanics can be described by local hidden variable theories, the previous inequalities must hold true. However, as is demonstrated in this notebook, these inequalities can be violated in a quantum computer. Therefore, quantum mechanics is not compatible with local hidden variable theories. If you want to learn more theory, explore Entanglement in Action with John Waitrose. You will create an entangled pair between two qubits in a quantum computer by creating the Bell state psi plus. Using the estimated primitive. I don't know. I don't know what's going on here. This is I don't know. I don't know what's going on here. And they're using a library, Qiskit, quantum circuit.
The third and final example that we'll cover in this lesson is not a protocol, but a game known as the CHSH game. When we talk about a game in this context, we're not talking about something that's meant to be played for fun or sport, but rather a mathematical abstraction in the sense of game theory, for instance. Mathematical abstractions of games are very commonly studied in economics and computer science, for instance, and there's quite a lot of value to be found in this abstraction. So games are not all fun and games, as it turns out, although it is fun to think about them. In this particular case, what we have is essentially a thought experiment that can be described in a pretty intuitive way as a game. The letters CHSH refer to the authors, John Clauser, Michael Horn, Abner Shimoni, and Richard Holt, of a 1969 paper where the example was first described. They didn't describe it as a game, in fact, and it's pretty common to refer to this example not as the CHSH game, but rather as the CHSH inequality. For computer scientists like me, however, it's just very natural to describe it as a game. I've already suggested that mathematical abstractions of games are both important and useful, and there are many different categories of games that can be considered. The CHSH game is an example of a class of games called non-local games. Here's the setup in general for a non-local game. We have two players, Alice and Bob, who cooperate as a team, so they either win together or they lose together. This means that they have no incentive to act selfishly, so it's essentially the opposite extreme to zero-sum games, which are purely competitive. Here, the game is purely cooperative. There's a third entity called the referee. The referee isn't a player in the game, but rather the referee runs the game. And in fact, you can think about the specification of a particular instance of a non-local game and the specification of a referee as being equivalent. There's a critically important constraint that's placed on Alice and Bob, which is that once the game starts, they're forbidden from communicating with one another. They can agree beforehand on whatever strategy they...
I don't get it. The simplest way to prove something so crazy is with endless complexities. It's like it's everyone who wants to demonstrate this crazy feature of the universe needs the examples are so abstract.
They choose, but no communication is allowed between them during the game itself. If you like, you can imagine the game taking place in a secure facility of some sort, as if the referee is playing the role of a detective and Alice and Bob are suspects located in different rooms in a police station. But another way of thinking about the setup is that Alice and Bob are separated by a vast distance, and communication is prohibited because the speed of light doesn't allow for communication to happen quickly enough. If Alice tries to send a message to Bob, for instance, the game will be over by the time Bob receives it. The way a non-local game works is that first, the referee asks both Alice and Bob a question. Alice's question is labeled X, and Bob's question is labeled Y. In general, you can think about X and Y as being classical states from whatever classical states that you like, and in the specific case of the CHSH game, X and Y are bits. Alice and Bob must then provide answers. Alice's answer is labeled A, and Bob's answer is labeled B. And again, these answers can be viewed as classical states in general, and like the questions, they will be bits in the CHSH game. At this point, the referee makes a decision. Alice and Bob either win or they lose, depending on whether or not the pair of answers AB is deemed correct for the pair of questions X, Y that the referee asked. And I'll say a little bit more about this in just a moment. First, let's take a closer look at the referee to understand what it is that's potentially challenging for Alice and Bob in a non-local game. And what makes a non-local game potentially challenging is that the referee can use randomness to choose the questions X and Y. That means that Alice and Bob have uncertainty. They don't know ahead of time what question they're going to be asked, and perhaps more importantly, they don't know what question the other one received. And it's that uncertainty, together with the fact that they can't communicate, that presents a challenge. So it's similar to the situation where a detective interrogates two suspects in different rooms. If the suspects don't know what questions the other one is asked, it's much harder if they're guilty to keep their story straight. Now, I mentioned a short time ago that the referee makes a determination that Alice and Bob either answered correctly or incorrectly, depending upon the questions that they were asked. It's assumed that this determination is made according to some fixed rule, and you can consider any rule that you want, but whatever it is assumed that Alice and Bob know the rule, so at least they have a fighting chance to answer correctly. We'll take a look at the rule for the CHSH game in a moment, but we could consider a different rule, and we would have a different example of a non-local game. Some non-local games are interesting, and in fact, some are quite fascinating and mysterious to this day. And some aren't so interesting. That's just the nature of the non-local game model. Anyway, these are the two different things that are needed to describe a referee. How exactly are the questions chosen, and which answer pairs are correct for each possible question pair? If we have a description of those two things, then we have a description for the referee, and that effectively describes an instance of a non-local game. Now let's take a look at the CHSH game specifically. The way that the game is defined, or equivalently, how the referee is defined, is...
I'm actually on the edge of my seat. I can't wait to see if I can reproduce this. My intuition is yes. I mean, it doesn't look like it's going to be it's going to be even interesting. Because as far as I'm concerned, Alice and Bob were created with all the flips of the coin already coordinated between them. Alice and Bob memorized beforehand the randomness of the flips of the coin. So they're always going to be correlated. It's not even a challenge. Let's see.
Is as follows. First, as I've already mentioned, the questions and answers are all bits. So the referee sends a bit X to Alice and a bit Y to Bob, and they each respond with a bit. Alice responds with A, and Bob responds with B. The way the referee chooses which questions to ask is simple. He chooses them uniformly at random. So a pair of questions XY is equally likely to be any one of the four possibilities: 0, 0, 0, 1, 1, 0, and 1, 1.
It doesn't matter. This is so straightforward. Alice and Bob have all the answers randomly picked but synchronized between Alice and Bob. They're always going to give you synchronized answers.
Finally, the rule that determines which answers win and which answers lose is that a pair of answers A, B is correct for the pair of questions x, y, if and only if the exclusive OR of A and D is equal to the logical AND of x and y. That may be a little bit easier to digest if we express those conditions in the form of a
Exclusive OR means either Alice or Bob, not both and not neither. That's all that exclusive OR means. Only 0, 1 and 1, 0 are correct.
table as you see right here. In the first column, we
Wait, 0, 0 is winning? And 1, 1 is winning? I don't get it.
have the four possible question pairs, and in the second column, we have the conditions on A and B that are required for Alice and Bob to win. In the first
So everything wins? These are all the options. A equals B, A equals B, 0 equals 1? What? Oh my god.
first three cases, the AND of x and y is 0. So the exclusive OR must be equal to 0 in order for them to win, and that's the same thing as saying that A and D must be equal, because A and D are bits. In the fourth case, the AND of x and y is equal to 1, and so the exclusive OR of A and D must be equal to 1 in order for Alice and Bob to win, and that's the same thing as saying that A and D must be different. So that's the CHSH game, and now we can think about different possible strategies for Alice and Bob and how well they can do in this game. Let's start by thinking about deterministic strategies, where Alice's answer A is a function of the question x that she receives, and likewise Bob's answer B is a function of the question y that he receives. And as it turns out, no deterministic strategy can possibly win every time. One way to reason that is simply to go one by one through all the possible deterministic strategies.
So they need to somehow coordinate between them. How are they ever going to coordinate? But I didn't get the winning condition.
Or of A and D is equal to the logical AND of x and y. That may be a little bit easier to digest if we express those conditions in the form of a table as you see right here. In the first column, we have the four possible questions.
Wait, the logical AND or the logical XOR? Didn't he say exclusive OR?
Of answers A, B is correct for the pair of questions x, y, if and only if the exclusive OR of A and D is equal to the logical AND of x and y.
Oh, if the exclusive OR is equal to the logical AND? What? Oh, loses. Oh my god, this is so confusing. The questions and answers are all bits. Okay, the questions x and y are chosen uniformly at random. A pair of answers wins if A, what is this? Is this A and B equals A XOR Y? A and B is the answer. The questions are X and Y, and the answers are A, B. So X XOR Y. So if the question is 1, 1, oh my god, this is so confusing. If it's 1 XOR 1, that's false. 1 XOR 1 is false. So this is A and B. So they need to coordinate. So Alice and Bob need to give an answer. In order to win, they have to do this. So, for example, if the question is 1, 1, 1, 1, 1 XOR 1 is false. So it's 0. 1 XOR 1 is 0. So 0, 0 and 0, 1 and 1, 0 are correct answers, but 1, 1 is an incorrect answer. But Alice and Bob don't know what the other is answering. They know X and Y. So all they need to do is, right, they can conspire. You agree that they can conspire ahead of time. So this is X and Y, right? There's only these four possibilities. And they, in order to always win, let's say they conspire to always win. So all they need to do is, when the question is 0, 0, 0 XOR 0 is 0. One is this, is, let me see, what do you call this?
0, 1, 1, 0, and 1, 1. Finally, the rule that determines which answers win and which answers lose is that a pair of answers A, B is correct for the pair of questions x, y, if and only if the exclusive OR of A and B is equal to the logical AND of x and y.
Wait, okay. The exclusive OR of A and B is the logical AND. All right, this is logical AND, and this is exclusive OR. All right, I misread it. Okay. This is the... Why can't they write the sentence? Wait, we can do CC.
A, B is correct for the pair of questions x, y, if and only if the exclusive OR of A.
The exclusive OR of A and B, this is the exclusive OR of A and B, and this is the logical AND.
Is equal to the logical AND of x and y.
Okay, let's see
That may be a little bit.
So it's like this. So the logical AND 0, 0 is 0. So A must equal B. The exclusive OR, let's see. 0, 1 is 1. 0, 0 is 0. And 1, 1 is 0. That's correct. Okay. If the question is 0, 1, the logical AND of 0, 1, right? He said logical AND. 0, 1 is 0. So again, in order to get 0, you do A equals B. And 1, 0, again, it's the AND is 0, then this gives you 0. And the logical AND of 1, 1 is 1. The only way to get 1, 1 is A not equal B using the XOR. Okay, fine. So Alice and Bob know how to win, right? They just, right? The rules are known ahead of time. The rules are known ahead of time. So all they need to do is they need to decide for example, when the question is 0, 0, we need to be the same. So we'll both answer 0. When the question is 0, 1, we'll both answer 0. When the question is 1, 0, we'll both answer 0. And when the question is 1, 1, Alice will answer 0 and Bob will answer 1. So that's one way they can always win, for example. Now, you can also randomize it. You can randomize their conspiracy to win, meaning Alice and Bob can say the first time that we have, for the first question, or for the first time we have 0, 0, Alice is we're going to go for 0, 0. For the first time we have 0, 1, we're going to do 1, 1. For the first time we're going to have 1, 0, we'll do 0, 0. And for the first time we have 1, 1, we'll do 0, 1. For the second time that we encounter 0, 0, we'll do 1, 1. And so on. They predetermine ahead of time. They flip a coin. They randomize, but they conspire. So they'll always give you a perfectly winning strategy because they know the rules. All right, so I gave you the solution. Let's see if they get the solution.
A bit easier to digest if we express those conditions in the form of a table, as you see right here. In the first column, we have the 4 possible question pairs, and in the second column, we have the conditions on A and B that are required for Alice and Bob to win. In the first 3 cases, the AND of x and y is 0. So the exclusive OR must be equal to 0 in order for them to win, and that's the same thing as saying that A and B must be equal, because A and B are bits. In the fourth case, the AND of x and y is equal to 1, and so the exclusive OR of A and B must be equal to 1 in order for Alice and Bob to win, and that's the same thing as saying that A and B must be different. So that's the CHSH game, and now we can think about different possible strategies for Alice and Bob and how well they can do in this game. Let's start by thinking about deterministic strategies, where Alice's answer A is a function of the question x that she receives, and likewise Bob's answer B is a function of the question y that he receives. And as it turns out, no deterministic strategy can possibly win every time. One way to reason that is simply to go one by one through all the possible deterministic strategies and to check that every one of them loses for at least one of the 4 possible question pairs. Alice and Bob each have 4 possible functions to choose from. We saw those 4 functions in lesson 1, so there are 16 possibilities to check overall. Another way to see that is to think about the equations here on the screen. We're thinking about deterministic strategies where a and b are functions of x and y respectively. So for example, a of 0 represents Alice's answer when her question x is equal to 0, and a of 1 represents Alice's answer when her question x is equal to 1.
But I already gave you the answer. I told you a deterministic strategy how to win. No deterministic strategy can win every time. I gave you a deterministic strategy that wins every time. They pre-conspire. The answers have been randomized if you want, but predetermined. What is this? This is Alice. Gives, I guess, a 0. And 0, 0, 0, 1. 0, 0 gives you 0, 0, 1. I'm not sure what he's trying to do here.
These are the 4 equations that have to be true in order for the winning conditions to be met in each of the 4 cases. For example, if x is equal to 0 and y is equal to 0, then the exclusive OR of a and b must be equal to 0.
Then the exclusive, right, so this is 0 times 0 is 0. So we already said we need a must equal to b. So, okay.
Whereas in the case that x is equal to 1 and y is equal to 1, the exclusive OR of a and b must be equal to 1.
Yeah.
One way we can see that there's no way to choose the functions a and b so that these equations are all true is simply to take the exclusive OR of all of the equations. The exclusive OR of any binary value with itself is equal to 0, and so it follows that the exclusive OR of the left-hand sides is equal to 0. That's because we have 2 instances of a0, 2 instances of a1, 2 instances of b0, and 2 instances of b1. So XORing them all together gives us the final answer of 0. But if we take the exclusive OR of the right-hand sides of the equations, we get 1, not 0. So the 4 equations can't possibly all be true. At least one of them has to be wrong, and that will lead to a loss for Alice and Bob in at least one of the 4 cases. And so it follows, because the referee chooses the questions uniformly, that the probability for Alice and Bob to win using a deterministic strategy is at most 3/4, or 75%.
No, it's 100%. I don't understand. I don't see. I don't understand. What am I missing?
Be wrong, and that will lead to a loss for Alice and Bob in equations or of all of the equations. These are the 4 equations Alice's answer when 4 functions in lesson 1. Every one of them loses for at least one of the 4 possible question pairs.
At least now it's clear that she did not explain anything. I don't know what she was trying to do. I mean, I've never seen anything so ridiculously irrelevant. What is this? She was trying to explain something? What? What is this? I don't know what this is. At least he's explaining it. I'm not sure I agree with him, but what she was doing, how can anyone understand what she was trying to teach?
Y that he receives. And as it turns out, no deterministic strategy can possibly win every time. One way to reason that is simply to go one by one through all the possible deterministic strategies and to check that every one of them loses for at least one of the 4 possible question pairs. Alice and Bob each have 4 possible functions to choose from. We saw those 4 functions in lesson 1, so there are 16 possibilities to check overall. Another way to see that is to think about the equations here on the screen.
No. I'm assuming this is Alice's answer. This is Bob's answer. This is exclusive OR. We said this is the winning. Winning is Alice XOR Bob is equal to X and Y. And this is what this is the winning. All right. And this is deterministic strategy. All right. So Alice gives 0 and Bob says 0. 0 XOR 0 is 0. 0 XOR 1, XOR is exclusive OR. 0 XOR 1 is 1. So I don't understand what's going on here. 1 XOR 0 is 1. And 1 XOR 1 is 0. So I don't know what's going on. Maybe Alice gives an answer to the question. The question is 0. The question is 0, 0. I don't know.
We're thinking about deterministic strategies where A and B are functions of x and y respectively. So for
A and B are functions of, oh, okay. So A is a function of 0. So given 0, 0, this is the question 0, 0, 0, 1, 1, 0, 1, 1. These are the questions. So, and the answer should be 0. Given 0, 0, right? The and of 0, 0 is 0. The and of 0, 1 is 0. The and of 1, 0 is 0. And the and of 1, 1 is 1. Okay. So the answer that Alice gives, XOR the answer that Bob gives, should be 0. And it's XOR. So, all right, but I already gave you the strategy, so this is a waste of time. I already told you the answer.
For example, A of 0 represents Alice's answer when her question x is equal to 0, and A of 1 represents Alice's answer when her question x is equal to 1. These are the 4 equations that have to be true in order for the winning conditions to be met in each of the 4 cases. For example, if x is equal to 0 and y is equal to 0, then the
So he says A is Alice's algorithm, how to answer. All right, but I told you, I don't need that. That's not what I would do. I would have Alice and Bob conspire to win before you separate them. I don't need Alice to sit alone, right? So, right, you said this is like Alice and Bob are separated. And now one investigator investigates Alice and the other investigator investigates Bob, and Alice needs to come up with a function A and Bob needs to come up with a function B. Yes, in that case, there's no winning strategy. However, what if Alice and Bob conspired before you separated them, right? Let's say there are 2 accomplices and they conspired a priori beforehand. They came up with the function A and function B to win. So function A and function B, they're always going to win. You have to be joking. This is all you got? This can't be real. This cannot be real.
exclusive OR of A and B must be equal to 0, whereas in the case that x is equal to 1 and y is equal to 1, the exclusive OR of A and B must be equal to 1. One way we can see that there's no way to choose the functions A and B so that these equations are all true is simply to take the exclusive OR of.
Okay, but you don't have to have function A and function B. You can have Alice and Bob have pre-conspired. It's not that Alice has a function based on 0. It's Alice based on the question 0, 0. Are you saying that you ask Alice X and Bob you ask Y? Is this the question? Okay, so this is a different question. The questions and answers are all bits. X, Y, A, B are 0s and 1. The questions X and Y are chosen uniformly at random. A pair of answers A, B wins for X, Y if. So you don't ask Alice why, or do you? I don't know. I don't know. I don't know. But this says that Alice doesn't know what Bob is being asked. So Alice needs a function. Okay, now if that's the case, that's difficult. So Alice doesn't know what Bob is being asked. But that's not what happens with entangled particles. Entangled particles, right? Each entangled particle ends up in a detector. The entangled particles have a correlated spin or something and a correlated random variable. Deterministic strategy. Alice, she doesn't have, you can't ask in a quantum system, Alice doesn't have a single variable. Alice gets a particle, and the particle is entangled. Okay, Alice, if Alice only knows, as you say, okay, yeah, we see here the referee gives Alice X and expects A, and gives Bob Y and expects B. So Alice and Bob don't share X and Y. Okay, in reality, X is an entangled particle and Y is X and Y are not independent. X and Y are entangled. And A is a pseudo-random measurement of X. So I don't know. This, yeah, this you're right. There's no way to win this game. I don't see how I can win this game. But this has nothing to do with the quantum system with entangled particles. This is a complete misrepresentation of a quantum of an entangled particle. Nothing here is entangled. You disentangled X and Y. This is you're assuming that X and Y are disentangled, but in reality they will be entangled.
Of all of the equations. The exclusive OR of any binary value with itself is equal to 0, and so it follows that the exclusive OR of the left-hand sides is equal to 0.
Wait, what is he? Is he suggesting a strategy?
Of A and B must be equal to 0, whereas in the case that x is equal to 1 and y is equal to 1 of x and y respectively. So, for example, A of 0 represents Alice's answer when her question x is equal to 0, and A of 1 represents Alice's answer when her question x is equal to 1. These are the four equations that have to be true in order for the winning conditions to be met in each of the four cases. For example, if x is equal to 0 and y is equal to 0, then the exclusive OR of A and B must be equal to 0, whereas in the case that x is equal to 1 and y is equal to 1, the exclusive OR of A and B must be equal to 1. One way we can see that there's no way to choose the functions A and B so that these equations are all true is simply to take the exclusive OR of all of the equations. The exclusive OR of any binary value with itself is equal to 0, and so it follows that the exclusive OR of the left-hand sides is equal to 0.
I don't know what he's saying now.
That's because we have two instances of A0, two instances of A1, two instances of B0, and two instances of B.
Right. So Alice, she cannot. I mean, let's say Alice says for 0 I give 0, and for 1 I give 1. I mean, I don't see how they can win this game. A of 0, let's say she says 0, and B for 0, he says 0. Let's say they always give zeros. 0, 0. A of 1 is 0, B of 1 is 0. That's not good.
B1. So XORing them all together gives us the final answer of 0. But if we take the exclusive OR of the right-hand sides of the equations, we get 1, not 0.
I don't know what I don't know what his proof is.
So the 4 equations can't possibly all be true. At least one of them has to be wrong, and that will lead to a loss for Alice and Bob in at least one of the 4 cases. And so it follows, because the referee chooses the questions uniformly, that the probability for Alice and Bob to win using a deterministic strategy is at most 3/4, or 75%. The fact that Alice
So Alice can she needs a function. A of 0 is equal to 0, or A of 0 is equal to 1, and A of 1 is equal to 0, or A of 1 equals to 0. And the same goes for Bob. It's they're always going to be randomizing. Yeah. There's a typo. Can win with probability greater than 3/4. Okay.
and Bob can win with probability 3/4 is quite easy to see, actually. If Alice and Bob both answer 0 all the time, for instance, they'll be correct 3 out of the 4 times. So Alice and Bob can't do any better than winning 75% of the time using a deterministic strategy. But what about a probabilistic strategy? Well, it turns out that using a probabilistic strategy can't help them at all. That's because every probabilistic strategy
50-50.
can alternatively be viewed as a random selection of a deterministic strategy, just like probabilistic operations can be viewed as random selections of deterministic operations, as we saw in the first lesson. The average is never larger than the maximum, so it follows that a probabilistic strategy doesn't offer any advantage in terms of winning over a deterministic strategy. And this even includes the possibility that Alice and Bob's random choices are correlated. So the bottom line is that winning with probability 3/4 is the best that Alice and Bob can possibly do using any classical strategy, whether it's deterministic or probabilistic. The natural question to ask at this point is whether Alice and Bob can do any better using the quantum strategy. And in particular, if they share an entangled quantum state, which they could have prepared prior to playing the game, can that help them? The answer is yes, it can. And that is the point of the example, and that's why it's so interesting. So let's see exactly how Alice and Bob can do better in this game using entanglement. The first thing we need to do is to define a quantum state vector, psi theta, for each angle theta, as you can see here on the screen. So psi theta is equal to cosine theta times ket 0 plus sine theta times ket 1. And here, by the way, we're thinking about angles in terms of radians. So for example, here's the vector we get when theta is equal to pi over 4, which is 45 degrees. Cosine of pi over 4 and sine of pi over 4 are both equal to 1 over the square root of 2, so this is just another name for the plus state. Here's another example when theta is equal to 3 times pi over 8. And in case you don't happen to know the sine and cosine of 3 times pi over 8 off the top of your head, here's a table of the sines and the cosines that we're actually going to need throughout this example, and includes the ones that we need for this particular vector. Now, if we want to take the inner product between any two of these vectors, for angles alpha and beta, let's say, it's straightforward to do that. We only have real number entries in these vectors, so there are no complex conjugates to worry about, and we obtain the product of the cosines plus the product of the sines. And we can use one of the so-called angle addition formulas to simplify that. It's the cosine of the difference between the angles. And because the cosine function is symmetric around 0, it doesn't actually matter which order we take them in. If you don't have these sorts of trigonometric identities committed to memory, by the way, you're not alone, but you don't have to remember them, you can just look them up. This one does make sense, though, when you think about the geometric interpretation of the inner product between real unit vectors as the cosine of the angle between them. If we compute the inner product of the tensor product of any two of these vectors with the phi plus state, we get a similar looking expression, except that there's a square root of 2 in the denominator. This is the first time that the phi plus state has appeared in the context of this example, by the way, and we'll see exactly why we're interested in this particular inner product shortly. But for the moment, let's just observe that we obtain the same expression that we had for the inner product divided by the square root of 2. And so we can simplify as before. Next, we'll define a unitary matrix, U theta, for each angle theta, like you see right here. It's not difficult to check that this is indeed a unitary matrix. The key thing we need to recognize is that the vector psi theta is orthogonal to the vector psi theta plus pi over 2. And that makes sense, because if we rotate by pi over 2, which is 90 degrees, we get an orthogonal vector. If we then multiply U theta to U theta dagger, we get the identity
Yeah, I don't know these things. I never went too deep into them.
matrix. Intuitively speaking, what this matrix does as an operation is to map psi theta to ket 0 and psi theta plus pi over 2 to ket 1. At this point, we have everything that we need to describe Alice and Bob's strategy. First, just like we had for teleportation and superdense coding, Alice and Bob will start out by sharing an EBIT. Alice holds the qubit A, Bob holds the qubit B, and together the two qubits are in the phi plus state. Alice's actions are as follows. She looks at the bit x that she receives from the referee, and if x is equal to 0, she performs U0 on A, which happens to be the same thing as doing nothing because U0 is the identity matrix. If x is equal to 1, on the other hand, she applies U pi over 4 to A. After she applies one of the two operations, she measures A using a standard basis measurement and sends whatever result she gets to the referee. Bob does something very similar. His qubit is called B, of course, and he receives Y from the referee as opposed to X, but the key difference is that he uses different angles for his unitary operations. If y is equal to 0, he applies U pi over 8, and if y is equal to 1, he applies U negative pi over 8. And we'll see why these choices of angles are good choices shortly. It's not at all obvious. And here is a circuit diagram that expresses this strategy. Bob is on the top and Alice is on the bottom this time. Here is the EBIT that is coming in, and these are the unitary gates that Alice and Bob might or might not apply depending upon what x and y are. For this one and this one, we have gates that are being controlled either by the bit x or by the bit y. And for these two right here, we have what kind of look like control gates, except that the circle isn't filled in. And what this means is that if the control bit is set to 0, then the gate is performed. And if the control is set to 1, then nothing happens. So it's just like an ordinary control gate, except that the roles of 0 and 1 for the control are swapped. So effectively, Bob performs this gate right here if y is equal to 0. He performs this gate right here if y is equal to 1. And similarly, Alice performs this gate right here if x is equal to 0.
So I guess in the first hour, that's what he was teaching.
And this gate right here if x is equal to 1. So that.
And this chick skipped everything. It's so simple. It's so simple. Anyway.
Is Alice and Bob's strategy. And now we just need to figure out how well it works. For the analysis of the quantum strategy that I just described, we really only need two things at this point. First, the unitary matrix U theta is as you see right here. And second, we had this formula. We don't actually even need the definition of the vector psi theta anymore. These two equations.
I mean, if they're actually using an entangled particle, then an entangled particle, then it shares the information. I already proved that entangled particles are entangled. I know that we agree that they're entangled, but we can explain the entanglement. There is a hidden variable inside the particle, so it's coordinating the answers.
Equations are all we need. There are four cases to consider, starting with case 1, which is that x equals 0 and y equals 0. And if we look back at the strategy, we'll find that in this case, Alice performs u0 on her qubit and Bob performs u pi over 8 on his qubit. Remember, Alice is on the bottom and Bob is on the top, so the state that they obtain looks like this. And by expanding that out according to the definition of u theta, we get this expression you see right here. We don't need to expand that out any further because we have the other formula to help us out. And if we apply that formula for each of the four terms, what we get is this. At this point, Alice and Bob both measure. And here's a table that explains the distribution of the outcomes. We take the absolute value squared of the coefficients to get the probabilities, which happens to be the squares of the coefficients because the coefficients are all real numbers in this case.
All right. I mean, they're measuring an entangled particle. Alice and Bob are each measuring an entangled particle, meaning the particle has a shared measurement outcome. The measurement outcome is correlated. So that's the answer. What's the question? You have to be shitting me. You have to be shitting me. You have to be shitting me. I cannot believe that this is what you're trying to tell me. That's it? That's it? That's the Nobel Prize? You have to be shitting me. I don't believe it. So Alice and Bob are each measuring an entangled particle that I already proved is entangled? It's 100% entangled with a hidden variable, 100% correlated. It's 100% correlated. And they're sharing it. What else do you want me to say? Well, I don't understand. What? And you call this magic? You have to be shitting me. I can't believe this is. I cannot believe that this is the case. I cannot believe it.
If we make use of the sine and cosine values from earlier in the lesson, along with some symmetries, we can express these probabilities as we have right here in the last column. Now, what we really care about is the probability that they win. And remember that in the case that x and y are both 0, they win if a and b are equal, and they lose if a and b are not equal. If we calculate those probabilities, we find that the probability that a and b are equal is the sum of this number and this number, which is equal to 2 plus root 2 all over 4, which is about 85%. The probability that a and b are not equal is 2 minus root 2 all over 4, which is naturally 1 minus the quantity that we just calculated. So they win with probability about 85% in this case. There are 3 more cases to consider, but they're all very similar to this one. In the case that x equals 0 and y equals 1, Bob applies u.
So that's all I need to do? So in order to destroy the Nobel Prize, I need to reproduce this with a hidden variable? Without an actual quantum particle? I will show you that I can do just as well as I can give you a 100% winning strategy? This is so confusing. It's like everyone I listen to gives you a completely different explanation. It's like everyone gives you a completely different explanation, and You what? This is I don't believe it. Okay, this is unbelievable. How long have I been here? Just an hour. Hmm. 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 I'm trying to think. They win with probability 0.85. I don't know why they only win with 0.85. Why not 100% of the time? When you say that they have this entangled equipment, right, they can each decide on what angle they set the measurement to. So they can measure in exactly opposite direction. So they'll be 100% entangled, 100% correlated. Right? You're not telling them that they have. You're not limiting them to the equipment. What I don't get it. Like what's the limitation? Why is it only 0.85? I can give you 100%. I can give you 1. I can give you a winning probability of 1. Why are you only getting 0.85? Who determines these angles? What are these angles? What's the nonsense with these angles? I didn't watch this video from the beginning. Why do you have theta? Why not? Why don't you measure a complete correlation? Why don't you correlate the measurement completely, like either 0 or 180 degrees? Alice and Bob share an EBIT. I don't know what an EBIT is. I'm assuming it's an entangled bit. So she has a gate. Um, she she then measures A and sends the result to the referee. She then measures A. Alice applies an operation to A as follows. So if x equals 0, she measures at 0 degrees. If x equals 1, she measures at pi over 4. I would say she always measures at 0, and Bob always measures at 0. And now they're completely correlated. Now they can conspire to give any answer they want. And now let's see. Because so when she gets the part, every particle, and she measures, if she measures up, she knows that Bob is down. So she knows Bob's question, right? By her question, she knows Bob's question. So she measures the particle. She measures A, right? The particle, the E bit, measure A, right? She measures the particle, right? This is how they conspire. Bob and Alice conspire by measuring. Once she measures, let's say that this is opposite the opposite. So if she measures and she sees up, she knows Bob has down. Let's talk about 0 and 1. If the measurement is 0, this is not the question. The question is x and y. Right? She gets x, and she doesn't know what y is. But the particle, it actually has what does the particle have? Is the particle related to the question? I don't think it has to be related to the question. They need to conspire. Alice and Bob have conspired she knows they can use the shared particle, the entangled particle, they can use it to know about the other guy. But how does that help them? She sees the question is x. If x is 0, it doesn't tell her anything about y. How can she know anything about y? It doesn't matter. I mean, I agree that the particle is useful. I'm not taking away the usefulness of the particle. Wait, I don't have to argue this. I don't have to argue this. This doesn't prove anything. All I need to explain is the fact that the particle is entangled through a hidden variable. This is even more nonsense than I could imagine. All I need to explain is what I've already explained, that the particle, right? They're using an e-bit. I'm assuming an e-bit is an entangled bit. Okay, but the entangled bit, we're not questioning that it's entangled. We're using entanglement. Okay, I'm not denying entanglement. I'm just saying I can explain entanglement through a hidden variable. This has nothing to do with the question. This is completely irrelevant. This is even dumber than I thought. Oh my God, I'm going to lose my mind.
For the analysis of the quantum strategy that I just described, we really only need two things at this point. First, the unitary matrix U theta is as you see right here, and second, we had this formula. We don't actually even need the definition of the vector psi theta anymore. These two equations are all we need. There are 4 cases to consider, starting with case 1, which is that x equals 0 and y equals 0. And if we look back at the strategy, we'll find that in this case, Alice performs u0 on her qubit and Bob performs u pi over 8 on his qubit. Remember, Alice is on the bottom.
Yeah, everybody agrees that entangled particles are entangled. There's no magic. There is a hidden variable.
And Bob is on the top.
And you're just using the entangled bit. You're just using the entangled bit. I'm not denying that the bit is entangled. The bit is entangled. Okay, I'm not denying that. All that you're doing is you have a quantum computer strategy. Okay. This doesn't prove that there's non-locality or anything. You're using a quantum computer. Yeah. And so I didn't deny, I'm not denying that particles are entangled. I already explained how they are entangled through a hidden variable. You just have a computer that employs this strategy. There's no magic. It's a hidden variable. That's already been pre-explained. And you're just using that. You haven't done anything. You have done nothing. Zero. Zero. Absolutely zero to discuss the issue. You're not discussing the issue. You're building on the issue. But the issue can be explained two ways. Either hidden variable or um what's the alternative? Hey tycoon. Or the other option is telepathy. Yes, tycoon, what's up?
Hold on, why can't I put this on speaker for some reason?
I don't know. I don't know. Sometimes the universe conspires to poop in your
Yo, brother.
Yeah, man, what's up?
Not much, dude. My bad. I had to put the thing on speaker. I don't know why the fuck I couldn't do it at first.
Wait, tycoon. Wait, do we know each other? Are we friendos? Have we ever
Yeah, dude.
Let me add you as a friendo. Friendo. You are now a friendo. Let me send you a message.
Yeah,
Hi. I
shoot
mean,
me
the
a, shoot
name
me a dude.
sounds familiar. No, we've never exchanged private
Like,
messages. Okay.
yeah, no, I don't know why. I've been in here before, man. I've talked to you a couple times actually.
Awesome. It is my honor that you come here. Anyway, how can I be of service to you today?
Oh, dude, nothing major. I just popping in to say what's up, see what you're doing.
Hmm.
I had a pretty long night last night, so I just kind of woke up late, and then
Mm-hmm.
yeah, that's about it, dude.
So yeah, I'm doing quantum entanglement these days. I'm trying to disprove now the 2022 Nobel Prize for quantum entanglement.
Okay, well, we can start with that for sure.
Oh, you want to talk about it?
I mean, you can tell. I mean, if you want, you can tell me, like, because I don't know much about that. So it's like, if you want to fill me in on what you've been learning about or studying up, researching, like, yeah, dude, for sure.
Uh, I don't know. I mean, it's up to you. You're sure you're up to you're up for the task? It's like it's BS. It's total BS. Like I believe quantum entanglement is utter BS. It's a nothing burger. It's a big nothing burger. Have you ever had a nothing burger for lunch?
No, I don't. I've had bullshit sandwiches, but other than that, no, I don't think so.
Mm-hmm.
I'll tell you right
Anyway.
now what I need. I need to
Hmm?
fucking. I said, I'll tell you right now what I need, man. Is I want to go over to the store
Mm-hmm.
next door
Mm-hmm.
and get myself an orange juice.
Awesome. Wait, orange juice? That's like a lot of sugar. Why would you want that?
Get that. I don't know, dude, because like it's just something that I'm craving right now.
Are you fat?
Nah, dude. I weigh
Oh,
like 160.
okay. How tall are you?
Like 5'8", 5'9".
Hmm. Okay. That's not
Just
bad.
a regular old motherfucker.
That's good.
Yep.
Anyway, you want to go or you want to talk? What do you want to do?
Yeah, dude, lay it on me. Let's hear what you got going on.
All right. Or we can discuss anything else. I mean, are you good at math? How good? Like, are you good at math?
I'm alright. I mean, I did what I went. Um, I
Hmm.
mean, I did my college classes. Did like typical like college algebra, this that. I mean, I didn't do anything crazy.
College
Um,
algebra. That's good.
yeah, it's not too bad.
Oh.
I went to school for software
Mhm.
development, so I did my 2 years, got my associates.
Oh, you.
Um,
What language do you program in? Do you program?
not like I should, man. I definitely did. I definitely did quite a bit of it in school, but I mean, I learned everything from like object-oriented programming to JavaScript and Python stuff like that. C plus,
No way.
C
You
plus.
didn't. You did C plus plus? Really?
That's what they started with. Funny enough, actually.
Wait, then you must be old.
No, man, I'm 31.
Yeah, so like you went to school like 10 years ago?
No, actually, I went to school back in 2021.
Oh.
I want to say
And
the end of
they
the end of
did C++ as intro to computer science with C++?
yeah. If I'm not mistaken, I think that was one of the first coding classes
Wow, that's
to get
terrible.
the fundamentals. Yeah, it's pretty weird. I don't remember so much of it, but
Yeah.
yeah. I mean, it was definitely enough to give you a fucking headache.
Yeah, C++ is very difficult. That's very old. They might as well start with like, I mean, that's really old stuff. No, I would never start teaching anyone C++. That's like very advanced. No one
Yeah,
uses you only use C++ today for very like incredible edge cases. Like you have to be like for most projects I would not use C++. Not at all. Anyway, that's good. I'll try and get you up to speed on entanglement.
all right.
So you have a particle, an elementary particle, like a quantum mechanical particle. That's a given. Given. Start with the given, as they say. So, given, you have an elementary particle that, if you give it time, it will decay.
Okay.
And if and when it decays, it turns into two daughter particles. So you had a parent particle, and it poof becomes two separate daughter particles. So far, so good?
All right. Sounds good.
Okay. And then, also given that the parent particle was not spinning. Not
Okay.
spinning. All right. And also given that the two daughter particles are spinning.
Okay.
Okay. Now, we have something in physics, it's called conservation of momentum. Have you ever heard of that?
Yeah, I have. I have heard of that. As a matter of fact.
Okay. But there's also conservation of angular momentum. Have you ever heard of that?
I'm not so sure.
Conservation of angular momentum just says that if you spin around, or if something is spinning, then it's going to spin forever unless you apply a torque, which is like an angular force to stop it or to change
Sure.
its. So it's just like inertia. So just like you have inertia that right, according to Newton's first law of motion, if something is in motion, it has inertia and it's not going to change its motion unless acted upon by some force.
Okay.
So the same goes for angular inertia or angular momentum. That if something is spinning, you need a torque in order to change its spinning or stop the spinning or reverse the spinning. Anyway, so given that the parent particle was not spinning and that the daughter particles are spinning, what can you say about the direction of the spinning of the two daughter particles if we assume conservation of angular momentum?
Hmm.
So
I'm not sure.
so yeah, it's confusing. Um, but the answer is that the two daughter particles must be. I'll ask you a question. The two daughter particles must be spinning both in the same direction or both in opposite directions.
I would think in the same direction.
Hmm.
Maybe I'm not.
So
Guessing that's not.
actually the correct answer is the two daughter particles must be spinning in opposite directions so that the sum of the daughter particles spin is zero because the parent particle spin was zero. So in order to conserve angular momentum, anyway, it's really confusing. Quantum entanglement, it's a confusing topic. We can discuss anything else if you want.
Yeah, man. I mean, I find that pretty interesting.
Yeah, it's interesting because everybody is confusing themselves. It's so confusing that everyone believes nonsense, and it's difficult. It's very difficult to explain to people that everybody just misunderstands it. It's just a big misunderstanding. That's all it is.
Yeah, that doesn't give it any kind of like a relevance either.
Yeah, it's completely irrelevant. It's a big waste of money, and like there's trillions of dollars going into quantum computers and quantum nonsense and quantum this and quantum that, and it's all a waste of money. It's all a waste of money.
Yeah.
Yeah. Anyway, what else do you want to talk about? Whose side are you on? Are you pro Trump? I guess you're pro Trump.
I did honestly. I couldn't tell you because I think they're both goofballs. I
Really?
didn't even vote. Yeah, I didn't even vote, man. First off, I didn't really have the chance to because I didn't have a car that day. Because my car got repossessed the night before. Um, so
What? Your car got repossessed?
yep,
Why? Why? You didn't pay? You didn't pay your loan?
I was late on my payments
Why?
because I fucking was paying it all to rent and other things.
Oh my God. Do you have a new car?
I do. 2018.
What kind of car?
It's a Hyundai Sonata.
Yeah, that's a
It's not
nice
too bad.
car. Wait, a Sonata? Is that's like pretty big, right? I don't remember already. What size is a Sonata? It's like is it the biggest?
I'm
Is
not sure about that, but it's a four door. It's a sedan. Yeah,
it's
it's a four door sedan.
is it bigger than a Santa Fe?
I'm not sure, man. I'm not so caught up on those.
Anyway, no, you have to pay. You have to pay your loan on time. You can't play with that. It's gonna ruin your credit.
Yep.
And now you don't have a. Wait, did you get the car back? Did you pay it?
No, I've driven BMW before, and I got all my stuff out, and they're selling it at an auction. But I just turned around and went right back to the dealership and got another car. So fuck them.
They gave you another car?
They didn't give it to me, but yeah, I mean, I'm friends. I used to work at that dealership for a little bit over 5 years, so I'm pretty tight with the sales manager. Her name's Amanda Carroll, and I told her the situation. I just sat right down and I was like, "Look, dude, this is what's going on. My car got repoed. My credit's in the shit right now." She said, "All right, well, let's figure out. Let me run some numbers and I'll get it straightened out for you." I said, "All right, cool."
I mean,
Pulled up the Hyundai on the lot, and then yeah, that's it.
that's a
Payments aren't too bad. I said it was before. The
that's a
thing is like I
mm-hmm. What? What happened? Oh, you're muted?
damn it, sorry about that. Somebody
Yeah,
called me.
no
But
problem. Mm-hmm.
yeah, I just perks of having friends, doing your job, keeping a good reputation and stuff. So yeah, she said, "All right, let me get this straightened out for you." They let me leave with the fucking dealer tag on it without even. I've got $3,000 to put down for a down payment. She let me pull out of the parking lot with the car. As of right now, it's literally parked in front of my apartment. No tags, just a dealer tag and no down payment. She said, "Just let me know when you get the check and come back and we'll get it figured out." I said, "All right, cool." Gave me the keys, let me go. So
Wow, you're lucky. I don't know how you managed that. That's amazing.
like I said, man, I don't know. Sometimes it helps to know people, get
Mm-hmm.
keep a good reputation.
Mm-hmm. Yeah. Anyway, what else? What else do you want to talk about? So you're saying Trump is a goofball?
Yeah, he just blabbers, dude. I feel like he just talks a bunch of shit all the time. I mean, he was already your president. First off, where do you live at?
When I'm in the States, I'm in like New York City.
Oh, okay, cool. I live on the East Coast too. I live in Virginia. You know where that is?
Yeah, sure. I mean, we're pretty close. Virginia is like close to New York.
Yeah, it's about 5 hours. I took the China bus up there, man, to the city, one time, and with some friends, and it was probably about 4.5 hour drive, or probably about a 4.5 hour drive, something around there. But I mean, I was fucking hammered anyway, so it didn't really matter at the time.
Mm-hmm.
Yeah, we got on the bus at like 12. I think we left around. Yeah, I think we left at midnight, and then we yeah, just got up to fucking got dropped off in the city in Chinatown, obviously, and then went to the bodega, grabbed a beer, and then just walked around. So we got into the Airbnb, and then when we did that, um, yeah, I mean that was about it. We just fucked around for a couple of days, skated a bunch, went to Central Park. I just had fun, man.
Mm-hmm. Are you high right now?
No, I'm just laying down.
Mm.
I didn't sleep very good last night. I
Mm.
got up pretty late, or I went to bed late, and then I got up pretty late.
Mm-hmm. Anyway, whose side are you on, Israel Palestine?
Um, I don't know about Palestine's side, man. It's hard to say. All that shit's like I haven't really kept up on what's been going on there maybe in the last month or so.
Mm-hmm. What do you think about Iran? Are you keeping up with Iran?
No, man, I haven't.
What about Elon Musk? What do you think about Elon Musk?
I used to really like Elon, man. I think
Mm-hmm.
I never really felt any kind of bad way about him or anything. I mean, I know. Um,
Mm-hmm.
I mean, dude, honestly, I think he's a smart motherfucker.
Mm-hmm. Mm-hmm.
Granted, you know, um,
Mm-hmm.
I saw a podcast with him or some guys that I like watching, or I used to like watching. Um, and
Mm-hmm.
they told a story about one time when they actually went to Elon's house. That's pretty funny, man. It's pretty. I'd have to like send you the link to it, but pretty funny story. But yeah, they literally like went to his house and stuff and like met they said that he had like these two dogs, like they were real fucking weird. And
Mm-hmm.
they pulled up there, gates opened up, and then they hung out with him for the night,
Mm-hmm.
and it really humanized him a lot more, you know.
Mm-hmm. Whose podcast was it on? Lex Friedman?
No, so it's like this guy named Cody Ko and Noel Miller. Um, the podcast is called TMG Podcast.
Mm. Never heard of it. TMG. Never heard of it.
Yeah,
Anyway.
tiny meat.
Mm-hmm.
Yeah, Tiny Meat Gang. That's what it stands for.
Tiny Meat Gang. Oh, okay. Anyway, listen. I want to finish. I need to finish something and do something. Um. So I'm gonna hang up in a couple of minutes.
Yeah, cool, man. It was definitely good catching up.
Yeah, man. I'll see you around.
Do you have a lot of other people that come into this chat or no?
Lately less. Like it's like an off season now. Like these days I started going to politics and religion server and I create a room there and I talk to people there. But sometimes people come to my server too. Like last night, I had like a professor from Stanford visit me, and we talked about um, entanglement. And I have another friend that we talk about philosophy, and he came by. Yeah, people sometimes come by, and we have like interesting conversations. Sure.
That's cool, man. I've got a server. I got a couple servers. Nothing too crazy. My buddy and I, when I was in school, actually, we set one up so that we could have conversations about that, anything, any and all topics.
That's
And
good. Hmm.
yeah, we'd have people. We kind of pull people from other servers, man. We do like Wednesday night discussions or something like that.
Hmm.
I enjoyed it, man. Like we don't really do it much anymore, but um,
Hmm.
yeah, it was fun, man. I like doing all that stuff, but
Hmm.
yeah, lately, like he's been actually he's about to get married, I think, soon. So yeah, he's got his own things going on.
Hmm.
But we've talked about doing the podcast and whatnot, and um,
Hmm. Interesting.
one of these things. Yeah.
Awesome. Anyway, I gotta go. I gotta finish this thing, and I gotta go. So,
Yeah, good evening, man. I'll be
see you
around.
later.
I'll hit you in the
Yeah, I'll see you
DMs or
later.
something
All right, you too. Bye bye.
later, man.
Later. All right. I wanted to finish this and then cut the stream, take a break, and we'll continue. So I cannot believe that this is so nonsensical.
So the state that they obtain looks like this. And by expanding that out according to the definition of u theta, we get this expression you see right here. We don't need to expand that out any further because we have the other formula to help us out. And if we apply that formula for each of the four terms, what we get is this. At this point, Alice and Bob both measure. And here's a table that explains the distribution of the outcomes. We take the absolute value squared of the coefficients to get the probabilities, which happens to be the squares of the coefficients because the coefficients are all real numbers in this case. If we make use of the sine and cosine values from earlier in the lesson, along with some symmetries, we can express these probabilities as we have right here in the last column. Now, what we really care about is the probability that they win. And remember that in the case that x and y are both 0, they win if a and b are equal, and they lose if a and b are not equal. If we calculate those probabilities, we find that the probability that a and b are equal is the sum of this number and this number, which is equal to 2 plus root 2 all over 4, which is about 85%. The probability that a and b are not equal is 2 minus root 2 all over 4, which is naturally 1 minus the quantity that we just calculated. So they win with probability about 85% in this case.
Mm-hmm. Mm-hmm.
There are three more cases to consider, but they're all very similar to this one. In the case that x equals 0 and y equals 1, Bob applies u negative pi over 8 rather than u pi over 8. The values in the formulas change.
It doesn't matter. They're using a particle, a quantum particle that we know is entangled. You're assuming entanglement. You're not analyzing entanglement. You're building on entanglement. You are saying nothing about how entanglement works. You're not taking a position if entanglement is built on a hidden variable or on telepathy. You're not taking a position. You are orthogonal. You are irrelevant to the actual discussion.
Change somewhat, but we end up with exactly the same probabilities that we had in the previous case. When x equals 0 and y equals 1, Alice and Bob still win when a and b are equal. And so we have exactly the same winning probability as before. In the third case, when x is equal to 1 and y is equal to 0, we have a similar situation. The angles are different, but they have.
I'm not denying that entangled particles are entangled. I'm not denying it. The question is that you're not addressing is how does entanglement work? You're not addressing the question.
Have exactly the same relationship to one another, and in fact, we do get exactly the same vector that we got in the previous case.
This is a complete waste of time. I can't believe people are getting salaries for this.
So the probabilities are the same, and so is the winning probability. The last case is a little bit different, as we might expect, because the winning condition is different in this case. When x and y are both equal to 1, Alice and Bob win when a and b are different. The basic method is the same, although the angles are different. This time we get this vector right here, And you can check that by going through required subtractions. The probabilities do change finally. And if we look up the values that we need, we see that the probabilities have effectively swapped positions from before. So this time it's the probability that A is not equal to B that is the larger of the two.
Yeah, you're using entanglement. No one is denying the entanglement.
But that's good because in this case, Alice and Bob win when A and B are not equal. So once again, they win with probability approximately 85%. Given that they win in every case with the same probability, which is 2 plus root 2 all over 4, or about 85%, that's the probability that they win overall. That's better than any classical strategy can do for this game, and that's what makes it interesting.
No, it's not interesting. It's not interesting. It's not interesting. What do you mean classical strategy? It's not a quantum strategy. There's no strategy. What are you talking about? You're allowing them to share, to have a shared strategy. You're saying, can they have a shared strategy? Okay, if you're allowing them to have a shared strategy, then they can use it just like you showed, right? If you're correct and they can use a quantum strategy to improve their odds of winning, fantastic. That has exactly 0.0 to do with the question. What is the nature of entanglement? You said nothing about what is entanglement. You said nothing about nature. You said nothing about the nature of reality. You're wasting everyone's time. What are you doing? What are you doing with your life? You're wasting your life.
This happens to be the optimal winning probability for any quantum strategy. You can't do any better than this using any entangled state. That fact is known as Searlson's inequality. It's named for Boris Searlson, who first proved it, and to my knowledge was one of the first people to describe this example as a game. In case the analysis that we just went through seems a little bit mysterious, it's
mysterious?
Possible to think about it geometrically, which might be helpful to give you a better sense for the choice of the angles. Specifically, if we use the formula that you see right here, which we can easily deduce from the expressions we already found for the inner products involved, then we can alternatively express the probabilities of the different possible measurement outcomes in the 4 cases as follows. First, if xy equals 0, 0, then these are the probabilities of the various measurement outcomes, and you have to either think back or look back at the analysis that we just went through to conclude that using our formula. Over here, we can see the different state vectors drawn as they were before, and the color coding here is that blue corresponds to the outcome 0.
I mean, it's great. It's great for this game. Yeah, I mean, it's just, I mean, you might as well have literally shared some random variable between Alice and Bob. What's the difference between allowing them to share a random imagine you allowed them to share a random variable. For every answer, they could share a random variable. For every question X and Y, let's say you allowed them to share a random variable. Right? It's the same. It should be the same. Right? Because that is what an entangled particle is. At best, an entangled particle gives you an entangled measurement. Some random entangled measurement. All right? It might as well be a random variable that is shared between Alice and Bob. So you're welcome. Roll the credits. I don't know what else to say. Don't waste my time.
And red corresponds to the outcome 1. You can see that the angle between the blue vectors and the angle between the red vectors is relatively small. It's pi over.
I don't know. I mean, they're obfuscating. This is. I don't have any other explanation except for they're so deeply entrenched in the math and the Dirac notations and all the calculations that they forgot that they're assuming entanglement. They're not analyzing the nature of entanglement. They said nothing about the nature of entanglement.
Over 8 in both cases. So the cosine is relatively large. And that means that the probability that the two outcomes are equal is relatively large. In the case that xy equals 0, 1, it's a similar situation. The angles between the vectors having the same color is small, so the probability of equal outcomes is, again, relatively large. The third case is similar. And in the fourth case, when xy equals 1, 1, something interesting happens. This time, just by the way these vectors have been chosen, we see that the angles between vectors having the same color are relatively large. And specifically, the angles are 3 times pi over 8 in both cases. This means that the probability that the measurement outcomes is equal is relatively small. But this is the one case in which Alice and Bob win when their answers disagree. So it's what we want. Once again, here are the vectors. When xy equals 0, 0, when xy equals 0, 1, when xy equals 1, 0, and when xy equals 1, 1. And perhaps this geometric picture is helpful in building some intuition for how the strategy works and why these various angles were chosen in the way that they were. To finish off the lesson, I'll make a few brief remarks about the CHSH game. First, as I've already mentioned, this example isn't always described as a game. In the physics community, for instance, it's more common that the example is described simply as an experiment rather than a game, and Alice and Bob are viewed as being detectors rather than players. The basic idea of an experiment like this, where entanglement leads to statistical results that are inconsistent with any classical description, or more generally any theory based on so-called local hidden variables, is due to John Bell, the namesake of the Bell states. And so people often refer to experiments of this sort as Bell tests. Sometimes people also refer to Bell's theorem, which can be formulated in different ways, but it basically says that quantum mechanics is not compatible with so-called local hidden variable theory.
What are you talking about? What are you I don't even know what you're saying. What are you talking about? This has nothing to do with how entanglement works. This is very similar to what Zabin said. I mean, Zabin also says this. But it doesn't matter what Zabin said. This is irrelevant to the question that is interesting, namely, how does entanglement work? There's two ways to explain how entanglement works, and you're saying exactly nothing about that. So you're saying nothing about the nature of reality. Nothing. And so are you, young lady. You said nothing. This test says nothing about reality. Everything you said, the weirdest, weirdest, beardish, geardish, nothing, nonsense.
The CHSH game, or inequality, is essentially a very nice and clean example of a Bell test, and you can think about this example as a proof or a demonstration of Bell's theorem. The second remark.
What is Bell's theorem? What is Bell's theorem? Please tell me. What is his theorem? What is his theorem?
Is that the CHSH game offers us one way to experimentally test the theory of.
Zabin said that even Bell got lost in the math. Even Bell doesn't know what he's trying to say.
Quantum information is an accurate theory. We can actually set up experiments that implement the CHSH game, including the sort of strategy based on entanglement.
But I don't want to quote Zabin because she says entanglement is important. What is entanglement important for? What is it important for? It's just a shared random variable. Who cares? There's nothing important about that.
Entanglement that I just described and see if it works. And it does. This provides us with a high degree of confidence that entanglement is real. And unlike the
entanglement is real, no one says entanglement is not real. This has nothing to do with the question.
Perhaps vague or poetic ways that we try to come up with to explain entanglement, the CHSH game or experiment.
You're not trying to explain entanglement. You said nothing about entanglement. You assumed entanglement, which is fine. You did not discuss entanglement. You're building on entanglement. That's meaningless. No one denies entanglement.
Gives us a concrete and testable way to observe entanglement. If that sounds important, it's because it is. And the 2022 Nobel
It's not. No, it's not. There's nothing important.
Prize in Physics acknowledges exactly this. The prize was awarded to Alain Aspect, John Clauser, who is the C in CHSH, and Anton Zeilinger for experiments with entangled photons that established the violation of Bell inequalities. Or, in other words, that showed that quantum strategies of the sort that I described actually work and outperform clock.
So what? So what? Outperform random? It's an entangled particle can be used to outperform not entangled particle. Yeah. So did anyone deny that the two particles can be entangled? Wait, we have comments. 1 second. Let me see. The predator. Okay, the predator. Nothing at all. Nothing at all. He thinks it's just a game. Who thinks? It doesn't matter. These people are assuming all over the I don't know what you're talking about. Maybe you understand that. I don't know. I can't give you credit if you don't tell me whose side are you on and why.
Classical strategies. If you're interested in learning more about this, I encourage you to check out the video.
There's nothing to learn about anything. You said nothing. This is utter nonsense. How is everybody so confused by this nonsense?
On Bell's theorem by my colleague Olivia Lanes right here on the Qiskit YouTube channel.
This is the colleague Lydia Lenz. What's this girl's name? What's her name?
Hi, my name is Olivia Lance from IBM Quantum, and I'm here.
Yeah. Alicia Lance Quantum? Your name is Alicia Lance Quantum?
Hi, my name is Olivia Lance from IBM Quantum, and I'm here today to.
From IBM Quantum. Alicia Lance. Is she Greek?
And finally, the topic of non-local games more generally is truly fascinating, and it's an
There's nothing fascinating. I mean, it's a nice mathematical game. Sure, okay. I find nonsense confusing. I mean, sure. I mean, they're able to confuse you. Like, in the beginning, I was listening. I said, "There's no way I'm going." I was listening to her. I said, "Jesus Christ, I'm not smart enough to understand what the heck she's talking about. There's no way I'm going to understand it." Okay, yeah, I still don't know what she's talking about. I don't know what she's talking about, but she gave the link. I clicked on the link. I came to this guy, and it's literal nonsense. Literal nonsense. Literal nonsense. How could all these people waste everybody's time? And they built a quantum computer with billions of dollars. They waste so much money. So much money down the drain for nothing. This is unbelievable. What? I'm not smart. I'm not smart. I'm not smart, but you're even dumber than me. How can you be dumber than me? How? You're not dumb. You're not dumb. You're not dumb. Why are you dumb if you're not dumb? Oh my god. Oh my god. Humanity is doomed. Guaranteed.
an active area of research that brings together physics, computer
There's nothing to research here. There's nothing to research here.
science, and pure mathematics, and there are still many interesting questions about non-local games
There's nothing interesting. It's boring. It's nonsense.
that remain unanswered to this day.
Ask me, I'll tell you. Ask me, please. Ask me. Ask me. Ask me, I'll tell you anything. I'll tell you everything. Just ask me, what's the question? Like what you just did? You wasted everybody's time. There's nothing practical. It's nothing more than a shared random variable. Alice and Bob have a shared random variable, and they used it in a game. Congratulations, right? Me and you agree on that. That's it. We agree on that. All that a quantum computer gives you is a shared random variable. That's it. Nothing else. You're not going to tell me that it's more than a shared random variable. Nothing else. Nothing else. Nothing else. Nothing else. That's it. What are you going to do with a shared random variable? What are you going to do with it? What are you going to do with it? Let me see. How can they be dumber than you? I'm not smart. I am not smart. I am dumb. I am dumb. But they are dumber. This chick, I'm dumb. I admit I'm dumb. I'm a dummy dumb. I'm as dumb as they come. But she's dumber. How? How can you be dumber than me? How? The same goes for you, sir. I don't know. I don't know. I don't know. Incredible.
And that is the end of lesson 4, as well as the end of unit 1 of the series on the basics of quantum information. The first lesson explained how quantum information works for simple.
This is the end of lesson 4, unit 1, and there's more units. There's more units. There's more units. They're not done wasting our time. But I thought you were a rocket a rocket surgeon. Basically, I'm a rocket surgeon. Yeah, that's, I might as well. I don't care. I'm a garbage man. I'm a poop man. I don't care. I'm not smart. I don't need to be smart. You just need to be honest. One thing I'm honest. I try to be honest. So that's it. I don't know what else to say. I'm honest. I'm not smart, and this guy is is dumber than I am. Incredibly enough. Unfortunate, and very unfortunately for humanity.
Single systems in isolation, and the second lesson explained how quantum information works for multiple systems, which pretty naturally emerges from how it works for single systems.
Oh my god. Oh my god.
The third lesson introduced the quantum circuit model of computation, and in the fourth lesson, we took a look at 3 important examples that illustrate things we can do with entanglement. Along the way, we saw
Entanglement. 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 The magic of entanglement. The magic. The magic. Entanglement. Give me money. Give me money. Pay my salary. Give me money.
some very important mathematical concepts, including tensor products and inner products.
Oh my god. Oh my god.
Observe some fundamental limitations of quantum information.
They give it names. Quantum information, quantum computing, it's quantum BS. Quantum BS. That's all it is. Quantum BS. You're wasting, congratulations. You've wasted everyone's time. Congratulations. Everyone is now dumber than we were before we listened to you. Congratulations. Thank you. Are these tutorials lectures free or do you have to sign up? No, I just clicked on the link. You go to this chick's her video and then you click on this link and then you kill yourself. You end up here and you want to die. They show you this math and then you know you're dumb because you don't understand this math. You don't need to understand the math. Everything sits on top of a shared random variable. That's all it is. There's a shared random variable. That's all that they agree that is all that a quantum entangled particle is. You know what isn't BS? Quantum memory powered by 8x world memory. Dominic O'Brien. Yeah, basically. Oh my god. Every time I start listening to one of these idiots, like in the beginning, I think, oh my god, I'm so dumb. There's no way in the world I'm going to listen to this advanced math and circuits and advanced math and circuits and Dirac notations and this and that. I'm never going to understand it. And then towards the end, I begin to understand and I realize, oh no, it's just BS. It's just very well obfuscated, utter BS. That's all it is.
I hope you'll join me for the next unit of the series, which will be on quantum algorithms, where we'll focus on
quantum algorithms. Can you believe it? Quantum algorithms. What about quantum pooping? I want to learn how to quantum poop. I want to go to the pooper and quantum poop. What unit is that? What about quantum? What else? What else can we quantum do? Oh my God! Quantum eat lunch. Let's go quantum eat lunch. Let's go quantum sleep. What about quantum sleeping? What unit is that?
the question of what computational advantages quantum information offers.
Nothing. There's no advantage from quantum computation. There is no such thing as quantum computation. It's just a shared random variable. Congratulations. Roll the credits. How come you are streaming alone? I was streaming this with someone. I sent him home so that I can finish this and go poop. And then, quantum poop. No, actually, I need to quantum pee.
Goodbye until then.
Goodbye until then. Goodbye. And look at all this math with this notation and this notation and the CHSH and look at this. Look at my math. Oh, look at this. Yeah, it's nonsense. It's BS. The whole thing is utter BS. I have quantum super sleep where I'm awake and asleep at the same. Basically, you win the predator, you win. Anyway, ladies and gentlemen, I'm so sorry for wasting your time with this garbage nonsense. I'm honestly sorry. I'm sorry. I'm sorry, humanity. I'm sorry that we are doomed because this is the best. This is the Nobel of 22. The Nobel Prize of 22. This is the Nobel Prize. Bell's inequality. The Bell's inequality. The weirdest theorem in the world. The weirdest. It's so weird. It's so weird. Nobel Prize. Give me money. Give me money for the Nobel. Yeah, it's BS. It's nothing. Absolute garbage. Yeah, I'm gonna go quantum pee and then quantum poop and quantum eat some. I'm gonna go eat some quantum gum. All right. It's only confirmed I was asleep when I wake up because of the observer effect. Yeah, basically, you know, you're gonna get a Nobel Prize. Be careful. I mean, they're gonna give you a Nobel Prize if you keep talking like this. Anyway, all right, ladies and gentlemen, let's just change the name because this was a very intense. This was very intense. This was intense. All right. So we reviewed. How do you spell reviewed? Reviewed IBM's. Thank you. I'm Don Fry. Hey, Don Fry. So we reviewed IBM's. What was that? What was that? None. IBM's CH whatever nonsense BS. We reviewed this. And what else did we do? Bell's inequality, weirdest theorem, Nobel Prize. This Nobel Prize, we can put that in. Nobel Prize 22. What else did we do? Estimated QPU usage 4 minutes. QPU, quantum. I guess quantum processing unit. It's a quantum processing unit. It's a quantum processing unit. It's a quantum. Give me money. Give me money because it's a QPU. It's a QPU. Give me money. Give me money. Okay, we can also introduce. Did we mention Bell's theorem? I can't believe it. I can't believe it. I just can't believe it. Bell's theorem. What else can we still have more characters we can throw into this nonsense. Requirements. Requirements. The Qiskit. SDK 1.1.0 or later. Oh, 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 look, map classical inputs to quantum problem. Oh my God, oh my God, oh my God. Entanglement in action. If you want to learn more theory, explore entanglement in action. Oh my God, you have to be a genius to understand that this is utter BS. Utter BS. Entanglement in action. Unbelievable. 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 I am speechless. 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 I'm sorry. I'm sorry. I'm sorry. Unbelievable. People get paid. People get paid for this nonsense. Unbelievable. 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 Absolute sad. Absolute sadness. Absolute sadness. Absolute sadness. What a waste. What a waste. What a waste of resources. What a waste of resources. What a waste of resources. It's only a matter of time before they silence us from speaking against quantum entanglement. They're not going to want us to speak against quantum entanglement and quantum superposition and the rest of the quantum utter BS. Anyway, that's it. So I'm gonna just save changes. Let me see the name. Reviewed IBM CHSH Inequality, Nobel Prize 22, Bell's theorem, entanglement in action. I don't know what to say. Terrible. All right. Aren't other fields also filled with complete nonsense too? Yes. Look at modern monetary theory and economics, etc. Yeah. Yeah, economics is filled with BS. I mean, I love economics. There's plenty of BS. And yeah, like every field that I've touched is filled with nonsense. I've done brain science, and most brain science is utter BS. Just complete and utter BS. I mean, these people are so smart and dumb at the same time that I'm speechless. They always leave me speechless. I don't know what to say. Terrible, absolutely terrible. Okay, everyone. I'm glad we went through this. In the beginning, I was listening to her and I said, there's no way. I wanted to give up so many times. I wanted to give up. So you saw me giving up again and again and again and again and again. I kept giving up. I said, there's no way I'm going to understand what she's talking about. And guess what? I still don't know what she's talking about. But all I can tell you, it's garbage nonsense. That I can guarantee. I guarantee you, it's garbage nonsense. I don't know if she understands what she's talking about, but at best, right? At best, all that she said is this. Is this guy. At best, what he said is shared random variable. At best. Right? That is what a quantum entangled particle is. It's a shared random state. That's all it is. Right? Everybody agrees that at best it's a shared random variable, right? They coordinate, at best they coordinate the measurement. At best they correlate the measurement. At best. There's nothing better than coordinating the measurement. Okay, at best it's this. At best it's this. At best it's this. At best it's a shared random variable. At best. So it's just a shared random variable. At best. All she's talking about, they have a shared random variable. At best. That's it. I don't know what else to say. Garbage waste of time. IBM, Google, and the rest of the quantum computing community. Feynman fell into this trap too. What? You are a rocket surgeon and brain scientist? I'm not a brain. I'm a brain. Yeah, I'm a brain scientist. I'm not a rocket surgeon, though. No, not a rocket surgeon. Anyway, unbelievable, as they say. Unbelievable. Okay, look. I'm glad we went. I'm so happy I didn't give up, because I was about to give up again and again. I was about to give up and I said, this is too difficult. I'm not going to make it. This is too difficult. She's scaring me. She has all this I don't know what she's talking about. I don't know what she's talking about. I don't know. I don't know. I don't know. I don't know. But then she said this. And I said, okay, this I understand. That's not hard. Okay, that's not hard. And I saw that it's towards the end. Okay. And then she said this. I said, oh, that's good. We have a script. That's good. And then she said that there's a link. And I said, oh, that's good. If there's a link, I'll go to the link. I went to the link. The link looked scary. It looked really scary. I didn't know if I'm going to survive this link, but I gave it a shot, and it's utter bullshit. It's BS. It's garbage, nonsense, waste of time. That's it. That's it. That's all it is. At best, it's a shared random variable. That's it. You're not going to tell me that an entangled particle is more than a shared random variable. That's all it is. At best. At best, you're not going to tell me it's more than that. It's not. You didn't say anything about the nature of entanglement, and all we know, all it is, it's a shared random variable. That's all. That's all. Okay, so you use a shared random variable, the quantum variable, the quantum strategy, quantum algorithms. Yeah, you used it. Okay. Okay, so what? It's just a shared random variable. That's all it is. Why are you wasting everyone's money and time? Poor IBM, poor Google, and Google built the quantum computer, and they're freezing it and schmeezing it and beezing it. But Jesus Christ, what a waste of money! What a waste of money, my God! But you're also a physicist and YouTuber. I mean, that's like three things right there. I know. Somebody should be paying me a salary. Give me money. Give me money. I want money too. I want money. I want more money. Give me more money. Yeah. Well, look, hopefully someone one day will watch this video and the video will survive, will not be taken down, and people will say, huh, so quantum computing is utter BS. Okay, yeah, that was our intuition all along. I mean, I don't know what else to say. I'm basically speechless at this point. So I don't know what to say. All right, I'm done. Let me take a break. I'll be back. Bye for now.